Hey everyone! So today we're going to be taking notes on earthquakes, and what you're going to do is you have a Google Doc that says earthquake guided notes, and it looks like the document I have on the right here. And wherever there's a highlighted number, you're going to type in what I have next to the corresponding number on the left in red. So, for example, one says instruments. You're going to write instruments on your guided notes on the right. So you're going to follow through with your notes as I go through my presentation. So before we get started on earthquakes, I just want to simply go over in a nutshell what it is. So we've learned about different plate boundaries. Convergent is where the plates come together. Divergent, they separate. Transform, they slide past each other. Well, earthquakes generally happen at where they slide past each other at a transform boundary. So when the plates of the earth are sliding past each other, sometimes I'm going to put my hands like this. Sometimes when they're sliding past each other, they get stuck on their way and they're trying really hard to get past each other. And when they eventually get unstuck, there's a surge of energy to Earth's surface. And that's what we experience as an earthquake, is that energy released from the point where they originally got stuck deep inside Earth's crust, reaching Earth's surface. So, how do we measure these earthquakes? Well, we have instruments called seismometers. Anytime you see the word seismic or any word that starts with SEISM, that refers to things that have to do with earthquakes. So, seismometers are instruments used to measure earthquakes, and they're sometimes called seismographs. So, if you look at this picture on the left, you have this rotating drum, which has kind of like a piece of paper on it, and you have a pen above it. And if there's no seismic activity happening, no like earthquakes or anything like that, the pen will just make a straight line. But as soon as an earthquake comes to the Earth's surface, it's going to record that on that rotating drum. So, for example, if I show you this seismograph right here, this is showing you what happens when the wave hits the seismograph. So notice the P wave comes, it shakes it, then an S wave comes and shakes it. There are multiple waves that come to the Earth's surface to hit the seismograph, and we're going to learn about them in a little bit. But as you can see, the waves come to Earth's surface, and every time a new type of wave shows up, you have more movement at it. So that is one where the seismograph is horizontal, but you can also have it where it's up and down. So in this example, again, you have a primary wave come, it hits the seismograph, and the seismograph is recording the different types of waves hitting its hitting Earth's surface. So the waves could be recorded on seismographs that where the drum is horizontal or vertical. And what are they recording on that little rotating drum? Well, it's called a seismogram. And it is a record of an earthquake. So it records the first wave that arrives, called the primary wave or P wave. Then it records the secondary wave or S wave. And then the surface waves, the last type of waves. It says, if you look at the bottom, the time it arrives. And the more intense the waves, the higher up and down it will go. So let's talk about the two main types of waves, okay? So primary waves and secondary waves. So P waves, in this one, you have the table already filled out, but please pay attention to this because this is, the main chunk of understanding earthquakes. So P waves, notice that P waves are called primary waves. Secondary waves are called S waves. So P and P, S and S. Think about primary school. You go to primary school before you go to middle school. So primary it happens first. Secondary it happens second. So primary waves, they arrive first. Secondary waves arrive second. So that, of course, means primary waves are faster. Secondary waves are slower because they're both coming from the same place where the plates get stuck and unstuck. the energy is coming from that point. So primary waves, since they arrive first, they've got to be faster. And what do they look like? These two waves look different. So primary waves are compressional waves, which means they move side to side like a slinky. And secondary waves are transverse waves, so they move up and down like a jump rope. And lastly, primary waves can travel through all Earth's interior. So inner core, outer core, mantle, and the crust. They can travel through everything, where secondary waves cannot because they can only travel through solids. Since secondary waves can only travel through solids, they cannot travel through the Earth's outer core because the Earth's outer core is liquid. Okay? So primary waves happen first, secondary waves happen second, and primary waves can travel through everything, whereas secondary waves can only travel through solids, so not Earth's outer core. So let me show you what these waves look like. So if you look at these GIFs I have for you here, the first one that I have here is this is what it looks like when a primary wave comes to the surface. So let's say right here where my cursor is where the earthquake happens, okay? What happens is when an earthquake happens, the primary waves go towards the surface of the earth. The waves of energy are going to make their way to Earth's surface. But look at the individual particles between where the earthquake starts and Earth's outer surface. What happens is the particles are moving up and down, causing that energy to be transferred to the next particle that goes up and down. Then the one on top of it goes up and down, kind of like a domino effect. The particles are transferring the energy. Notice that the particle itself is not going from where the earthquake happened to Earth's surface. It's transferring that energy to the next particle, and then the next one, then the next one. So the wave of energy makes its way to the surface of the Earth, but each individual particle just moves up and down, transferring that energy. So that is a primary wave. So it's moving like a slinky to Earth's surface, all right? You have the energy going up, then down, up, then down, up, then down to Earth's surface. That's a primary wave. A secondary wave looks like this next GIF right here, where the wave is eventually going to make its way to Earth's surface all the way up. But on its way to Earth's surface, the waves on their way just move side to side. So the particles just move side to side. So the first particle moves side to side, causing the next one to go side to side, the next one side to side, etc. And this has effects when it comes to Earth's surface. So if primary waves are going like a slinky to the surface, when they reach the surface, they're going to cause Earth's surface to bounce up and down. And then when secondary waves arrive second, they're going to go side to side and shake things side to side. But then after that, you have something even more intense that comes along. It's called a surface wave. So surface waves, they travel last. They come after primary waves and secondary waves, and they are the most harmful because, or towards human-made structures, because they move Earth's surface side to side like an S wave and up and down like a primary wave. So it causes all of this motion in different ways, which is very destructive towards human-made structures. So one of the ways we've learned about that is a surface wave is when we talked about water waves. So water waves are surface waves, and if you follow this yellow water molecule, one singular H2O molecule, even though a wave is bringing in energy towards the shore, it's not like the water molecules from way out at sea are suddenly finding their way at Earth's shore. They're transferring the energy, but the particles are going in a manner that's up and down and side to side, like this surface wave right here. So that's why they're most destructive when earthquakes have surface waves come to the surface, because you have the particles moving left and right and up and down. So it's very destructive. So yes, surface waves do happen with waterways, but they also happen with earthquakes waves. Okay, And a couple of quick words, aftershocks and foreshocks. So think about like foreshadowing, something happening before um, it's the main thing's happening. So a foreshock is a tiny earthquake before the main earthquake, and an aftershock is any tiny earthquake after the main one. So think of it this way: if you have two plates of the earth sliding past each other and they get stuck and then unstuck, it's not going to be a perfect transition from smoothly sailing, they get stuck, and then unstuck, smoothly sailing in their respective directions. So before they get stuck, there's going to be some foreshocks, and after they get unstuck, they're going to work out and get a few more little aftershocks afterwards. Okay, so how do we measure earthquakes? Well, we measure them on the magnitude scale and replace the Richter scale. And when you see the word magnitude, like orders of magnitude in math means that um, something is 10 times bigger than the last number. So a magnitude 1 earthquake and a magnitude 2 earthquake, it's not that the magnitude 2 earthquake is just 2 times stronger, it's 10 times stronger. Each number you go up the magnitude scale, it's going to go up 10 times by each one, each number up. So 9 isn't 9 times stronger than 1, it's immensely stronger. So how do we measure the strength of earthquakes? What is this magnitude scale all about? Well, it's two things. It's about the size of the waves that come out and how much damage is caused by the earthquake. So human-made structures, how damaged are they? So it's how much energy is released and seen on seismograms or seismographs, and how much damage is caused. So 9 is the strongest on the scale and 1 is the smallest. All right, and then two of the most important words for earthquakes are epicenter and focus. So the epicenter is the point on Earth's surface above where the earthquake originates, whereas the focus is the actual point where the earthquake started, the point where the rock was stuck and then got unstuck. So in more scientific words than stuck and unstuck, the earthquake happens at the focus because that is where the crust has built up stress, and when it gets rid of that stress and the rock breaks free, that earthquake starts. The energy releases to the surface. So if you look at this picture here, the focus is the point where the earthquake originated, and then you have all these circles around it. That is the energy being released in every direction. And the point right above the focus on Earth's surface is the epicenter. But notice the waves go all over. That's why you don't have to be right above an earthquake to feel its effects. So epicenter is the point on the surface, focus is the point where the actual earthquake originated. Okay, so how do you find the epicenter, the point on Earth's surface above where the earthquake originated? Well, the most important thing is you need seismograms from 3 different seismograph locations. Then you need a P wave arrival time and S wave arrival time at all 3 stations, and you need a little reference table chart called the earthquake wave travel time chart. So this is what the chart looks like. If you take earth science in high school, you will see this chart to figure out how far away you are from an earthquake. So if you look at the bottom, it says the epicenter distance in 1,000 kilometers, and you have the P wave, which tells you what time it arrives on the left, and the S wave, what time it arrives on the left. These are minutes on the left-hand side. Notice that the P wave arrives first, so let's say we're 7,000 kilometers away from where the earthquake originated. It's going to happen at maybe like 10 minutes or something like that, all right? I'm not being too precise here. That's how long it might take the P wave to arrive from the earthquake if you're 7,000 kilometers away, whereas the S wave might take like 19 minutes to arrive. So this picture, I just want you to be able to see. You don't have to get any of this right now. But if you do take earth science in high school, you'll need to know this chart. So basically, all you need to know about this is with the P wave arriving faster and S wave arriving slower, that's why the P wave is lower down. because the P wave, this is the time it takes to arrive, and the S wave, it's going to take a lot longer for it to arrive. And the difference between how the times they arrive tells you how far away you are. Think of it this way. Don't worry about this for now. But basically, the further you are from the earthquake, the more time has elapsed between when the P waves arrive and S waves arrive. Okay. Then you have these 3 stations. Okay, to find an epicenter. How do you know, first of all, how far away you are from the earthquake? Well, if you use this chart and you figured out how long it took the P wave to arrive, the first line, and then how long it took the S wave to arrive, the second line, if you find that difference in time, you can find how far away you are, the distance. And then you go to this, you go to the map, and you can plot little circles of how far away you are. So let's say we're in Minnesota, and we figure out that we are 1,000 kilometers away from the earthquake. We know it's 1,000 kilometers away, but we don't know which direction. It could be north, it could be south, it could be east or west. So we could just draw a circle around it. So we know the epicenter of the earthquake is going to be 1,000 kilometers away from Minnesota, but we don't know where it happened. So if you have a second point, let's say in Michigan, it's 500 kilometers away. Okay, 500 in any direction. Well, look, these two intersect at 2 different points right here. So they intersect up top here and down here. That's great. So now we're down to 2 locations that the earthquake can be. That's why you need a third map. So let's say in Charleston, we know that it is 750 kilometers away. So we draw a circle 750 kilometers away, and it only intersects with the other 2 at this point right here, okay? So this point is called the approximate epicenter. That's why you need 3 points, because if you have 2, the circles only intersect at 2 places, but at 3, they all intersect at only 1 place, which is where the earthquake epicenter is. So that's just a very brief introduction to earthquakes. So we learned about seismometers, which is how you measure earthquakes coming in. We talked about P waves and S waves and surface waves. We talked about the magnitude scale. We talked about Earth's epicenter and focus, foreshocks and aftershocks. We talked about how to find an epicenter. You need 3 stations. You need to have the P wave and S wave arrival time and the chart. The chart shows you how long it took a P wave to arrive and an S wave to arrive. That difference in time will let you know how far away your epicenter is. Again, this chart, you don't need to know this year. When you take earth science in high school, you will need to know how to use it. Once you use this chart to find the distance of an earthquake away, then you go to your map, you draw a circle that is that far of a distance. So let's say you're in Minneapolis, that the epicenter is 1,000 kilometers away. Draw a circle 1,000 kilometers away in every direction. Once you draw your 3 circles, X marks the spot, and that's where the epicenter happened. So now you should be able to finish up your guided notes, and you can submit it on Google Classroom. And I hope that you all and your families are well. And thank you so much for watching this video on earthquakes.